In this part, we're going to do all the maths. Don't be terrified. I've redrawn the general schematic. We have a resistor RB. Usually it's a massive resistor. Think about it. We only want a tiny, tiny current here. So how do you limit the current? Shove in a giant resistor in there. This resistor is relatively small in comparison to this dude. And I've drawn it in conventional current. As I've said, across BE, the base and emitter, we will drop 0.7 volts no matter what. Well, as long as we have 0.7 volts being supplied. But basically there's two loops in the system. There's the red one and the black one. We're going to look at the red one. The red loop has to obey all laws of physics, including Kirchhoff's laws. Voltage supplied needs to be equal to the voltage dropped across the resistor, which also needs to be equal to the voltage dropped across BE. If you rearrange the equation, we can sub in a relationship for the voltage dropped across this dude. Well, we know Ohm's law. V is equal to I times R. Remember that when we're studying transistors, we can use Ohm's law with resistor behaviors, i.e. this dude will obey Ohm's law. This dude, This dude is a bit weird, so that is why we need to do maths. We sub in Ohm's law for the voltage drop across the resistor, rearrange the equation, and we have an expression for the baby current, the IB. That's really cool. That means that we're supplying a voltage, we know what it is. We know what the voltage drop across BE is. A classical diode, it's about 0.7 volts. And we know what our resistor is usually when we build our circuits. So without even measuring anything, we could calculate what the current is in our red circuit.